Welcome everyone for high performance computing. This is the second part of lecture 7 about distributed deep learning and applications. And in the first part of lecture 7, we basically introduced a little bit the foundations of distributed deep learning. We pulled together different pieces of different lectures we had before to make a comprehensive picture why basically for distributed deep learning we care more about one GPU. So we go in a multi-node setup, meaning we're leaving the space basically of one GPU with one memory space, and we have to communicate. Hence, the communication then needs to be supported by communication libraries, and we had the example of Nickel, for instance, for NVIDIA, which is sort of on the software side, but then we also learned with NVLink and NV switches, we have their support basically on the hardware in the NVIDIA setup. And this enabled us also in the example of the Summit HPC system, for instance, to have 6 GPUs on one node communicating very well together via this NVLink and NV switches. Now, today we want to then basically not only stop there in one node with many GPUs together, which is already a form of distributed deep learning. We also want to go to, multi-node setups involving much more GPUs. So not only, let's say, 6 per node, but really scaling up. And by doing this, we will also explore limits. So what happens to the batch sizes? You remember in epochs, we train with batches. And we will also explore a little bit the different functionalities that we enable basically distributed learning with. Like model parallel, data parallel, and there's even a more or less new approach or a combination, if you want, called pipelining. So hence, before we go into the material of the second part now in detail, let us just briefly review this part, because this is now important to understand the motivation behind all of this. And I think we have seen one of the ideas in the last part of the lecture that the large learning models, for instance, with 1 billion of learnable parameters, is really a space where you leave the, basically the space of one GPUs and need very many GPUs because of all this learnable parameters. In other words, large language models, as the name suggests, large transformers have many learnable parameters. And with this, these weights needs to be trained, and this needs lots of computing power. And by doing so, of course, we go in a distributed fashion, right? So we involve basically the power of high performance computing, having very good interconnects between all of these different nodes with many different GPUs. And that's one of the motivation, right? So kind of the model sizes are getting bigger and bigger. However, what we also explore, more and more in different areas of science and engineering is also the data. Right, so we see that more and more big data has really come into place. The data sets are increasingly in terms, of volume, of quality, and in this sense, we also see that really with the, availability really of more data that we have seen, for instance, in the satellite image examples. There's also another need of going out of the GPU space in terms of memory, right? So one memory is not enough of a GPU. Hence, we have to have more GPUs to actually digest the data that we want to use for training. And you see now in this particular graph here that if we combine this well with, let's say, cutting-edge transformer models on cutting-edge HPC machines, we come to a very good accuracy that is basically fueled with this large deep learning networks. And of course, the large language models are there as a premier or king examples, but this holds also true for remote sensing and other applications I will talk within the second part of the lecture. So this is incredible to understand the different, let's say, motivations. Again, I summarize them here. The learnable parameters, they will grow significantly, as we know already from the large language models in billions of parameters, but then also the data sizes. So in order to approach this problem, we already looked a little bit in the first part of the lecture on what we now basically formalize a little bit and will, basically define as a data parallel technique, because you can do also other techniques like model parallel. So here the idea is splitting up the data, right? And then basically have the training on multiple nodes in parallel. So the model is basically copied on each node. You see that here essentially, right? So this is the same model here on all of these different nodes, but the big chunk of data that we have, the data store modeled here, is then actually splitted up, right? And every time, these different nodes in this processing are actually then doing the learning. This is done via backpropagation, for instance, of a neural network model, taking the gradients then and update the weights of this particular model. But as the model should be in sync, of course, we then, as we learned already a little bit, leverage here MPI to do the average of the gradients. In updating the model then, we basically have the idea that we continue the learning on each of the different nodes, but of course use also then the MPI every now and then to synchronize and make an average across the nodes. Hence, something we already explored a little bit. The beauty is it is really well suited for parallelization to order, basically get a speed up out of this, which is important for us. So we don't want to parallelize just for fun, which is now one part. We want to achieve, of course, a speed up, so faster training. But we also will see that in one respect, we have a certain constraint there, bringing us also to the batch size problem, mini batches, and so on. So this is a terminology about the batches, which usually in a machine learning course will be much more explored. So here we take it as a point of going through the data, in different batches. And then, of course, when you have more and more, let's say, these data splitted, we talk about more or less mini batches and still doing the gradient descent, basically on these mini batches. And in the end, you have the benefit that it's a more accurate estimation, and it has usually a smoother convergence, and it basically can, with this, going also to larger learning rates, right? So in other words, when you have larger learning rates, you train faster and you trust more the gradient. So this is, you remember what we had in lecture 6, a little bit, the stochastic gradient descent going downhill on the error slope, basically. And then you basically have here with the, let's say, smaller or mini batches, a better idea of that you have trust in this. So, and you send these batches across the GPUs, compute on them, do a smaller training, if you will. But of course, many are in parallel. We come to this, of course, later. When we now think about it, now you don't involve just 3 GPUs here, as the, let's say, illustration suggests. We involve maybe 512 or 1024 GPUs, and we will see what happens. Hence, there's also limits we have to discuss, and the limits are basically also constituted a little bit in constraints in the learning, and also the idea that in some point of time, we as machine learners maybe not care only about speed up. That is nice to have faster training, yes, but we also care about the accuracy of our model much more. Hence, there's not really a trade-off, although it would suggest that faster training, you lose the accuracy, what's the point? You have to think about that AI usually has a purpose. This machine learning algorithms, deep learning algorithms want to solve an application problem. Hence, we will also look at some of the applications later. But this means we want to have the accuracy well or a low error rate of these models. When I just lose this by throwing more computing to it, then we also don't win. Hence, there's a certain constraint that whatever we do in this parallelization techniques here, data parallel, model parallel, and so on, we want to keep the accuracy as best as possible, and this is technically not possible when we scale up very much. Hence, there's a certain limit we will explore, but coming better maybe then to the idea of a data parallel approach, where we have the implementation aspects, which could be 2 different approaches. And one in the past often used was a parameter server one, where you have here, for instance, the idea on the right side, you see that in fact you have different workers working on a problem, doing their distributed deep learning on different parts of the data, as we just learned, so splitting up the data. And while doing so, we have one master implementing in a way the master worker paradigm that, this basically is where the gradients will be all then averaged at the servers, and then distributed again. So the same concept as we have seen essentially here, but here we didn't actually differentiate it between the, let's say, parameter master. And you can imagine in other, let's say, larger ideas of distributed deep learning, you have an example from Uber also describing this if you want, using Horobot at scale with data from the Uber that you probably also know from the cars and so on. So then you can also grow bigger in this. So essentially you have a multiple master and multiple worker paradigm here that you implement. And this is, of course, something which in a way um, can handle the load. And of course, this is our first concern. So if you have more data, we need more workers. If you have, let's say, bigger and bigger models, that means bigger and bigger gradient amounts and matrices, or maybe even one parameter server is not enough. However, to identify the right ratio then of workers to parameter servers is one of these challenges, right? This is manually done. It's actually quite a hassle, a little bit from the coding complexity as well, because you have to start these work and parameter servers. So in a way, you do this, let's say, parallelization partly yourself, while we can imagine already, having learned a little bit in the earlier lectures about the so-called message passing interface, that there are nice abstractions of these complexities, and maybe there's a possibility, and you know this answer already from the first part, of actually leveraging rather MPI in a smart way. Coming back to the collective functions, the one that we are most interested in is the MPI or reduce, which is not this one that you see here, but it's basically very similar, just implementing this MPI reduce then for all the processes at once. So everybody in the end gets a global sum, right? While here, you remember everyone in the communicator get automatically here the sum in the MPI reduce, as the example was. And by leveraging this communicator, we essentially with the MPI environment don't have this hassle anymore, like starting up the service with parameter service workers, etc., etc. But here we take and leverage the MPI runtime. And as collective operation, this is also very well implemented. And the way how it is then in the data parallel approach really used is the so-called MPI ring all reduce. So we keep still the idea of data parallel. So that's, inherent that you see on the top right. We have now data and we're putting that in the different devices, let's say NVIDIA GPUs as an example, but could be also, let's say, different devices where we have now the small amounts of data we train per worker as we did before, but you see and observe there is no parameter server anymore. Hence, the idea of using MPI now in the stepwise fashion you see here with this ring or reduce means that we use and leverage the buffer space in the moment where we send, also in receiving new updates in the next iteration. So you come then to the fact, and this is then the idea of this ring idea that you implement here, is that through using the buffers and sending around the average updates using MPI or reduce, you have a very efficient implementation. I have put this a little bit here in more detail because essentially you have a communication library that is already perfectly implemented to be of high performance, right? We learned this already in the beginning of the course through MPI. That is its main role. So distributing data. Hence, we're leveraging it here more precisely than for deep learning. And it involves communication, let's say 2 times n-1 times, depending of n, of course, how many nodes we have in the game. The 3 I always do here is basically just an illustration. Again, think about now we're going up to 512 GPUs. So, and how it works is then in the first iteration here that you would have essentially where you go once through it, you basically receive the values and as I said, updates to the buffers. And when you then essentially go another iteration through, you receive the values from others and replace what you basically had in your own node buffer. And with this, you have a sort of moving average ring that you see a little bit also in the colors here when you go through the ring. So I have here also a reference, if that's not clear to everyone, Needless to say, in this lecture here, we go a little bit more advanced, right? So definitely the topic of distributed deep learning is not the simplest one, especially if you now come up to more elements where machine learning is also inherently in. You will see the learning rate, the batch sizes, many of the machine learning aspects will drive some of the distributed deep learning aspects as well. So here we really combine a lot of knowledge on machine learning, deep learning, a lot of knowledge of high performance computing, and so on in order to make the point for distributed deep learning. And you can consider as one of the most, let's say, advanced topics that we have also here in the course. So I think here and there, it's maybe good to look again to some, basically references I put in here. And just to, also have now a different view on it. And you see that here, data parallelism, where the model parallelism, we introduce also now the idea of model parallel approaches to distributed deep learning. Needless to say, you would have one model, right? So there's now another way of doing it that you layer-wise can cut, right, on these different devices. So it's not anymore like you remember what we said here, the same model on all the devices. You train a little, average the gradients, and then you keep the model in sync, although basically it's there. Let's say there are also problems sometimes that maybe the model is so large that doesn't fit to memory, right? So then hence you can do a model parallelization techniques of essentially creating this layer independence aspect, which is a little bit shown here in this nice picture, which is actually also out of a very good paper. I would recommend you if you're really interested in the topic here, reference 23 from a colleague of mine, Thorsten Höfler, really expert in the field of HPC and also distributed deep learning. So there's a huge, let's say, resource to really understand it, let's say, to the really down details. But of course, this would be not then anymore an introduction to HPC course. Here we would talk about really material which cover, let's say, a couple of lectures just on this, and we don't have that space here in this particular course. However, good reference. And when you now come to this model parallelism, I think it's sort of understood that these mini batches we talked about is actually now to all processors copied. So we don't have basically the idea of making this data parallel anymore. Hence, we have this model parallel. And then we use the data on all these different devices with fractions of the model, right? So, and of course, you can imagine that there's some bottlenecks again, or some elements where it's a bit more complicated. For instance, in the dense layers, right, where you have an all-to-all communication suddenly. So I think that's pretty obvious what model parallel stands for, contrast to data parallel. And many of the examples we have here and there are data parallel, but think in your head that sometimes the model might be so huge that actually model parallelism is necessary. In terms of deep learning frameworks now supporting all of this, we basically heard already a little bit about TensorFlow and Keras. And if you look in the scripts that you had in lecture 6 and that of your assignments, they are based on TensorFlow and Keras. And they are already having a, let's say, runtime that is already working with GPUs, so can leverage, let's say, a GPU apart from only CPUs, for instance, and also can basically run a little bit in parallel. I come to this in a moment, because TensorFlow, for instance, has its own implementation of this parameter servers that I was alluding to. Right? Even if that's maybe not the best, it's still already supported, and others extend this mechanisms then with different ways of doing rather the MPI implementation, for instance. Then Keras is a library on top. And again, when you look at lecture 6, for instance, on the code I was providing in the previous lecture, you see it's quite understandable from the sort of layer-wise architecture, which is quite nice in Keras, making it also a good tool, let's say, for learning, for training, because you have quite an analogy of the different layers that you have in deep learning and the functionalities, while TensorFlow, as the name suggests, is a little bit lower level, where you already, think about multidimensional arrays, tensors, matrices flowing through your neural network, right? So it's basically a bit of different abstraction layers. However, Keras is built basically then and uses then TensorFlow constructs, and TensorFlow itself has already, let's say, an engine leveraging GPUs. At the end, of course, this means CUDA. Now, extending this view, with a particular focus on distributed deep learning, there are other tools as well. So for instance, the Horowat approach that we were just, a little bit using here and there for getting the data parallel understood is essentially now this implementation where you use maybe different, let's say, deep learning packages with. So you can use it with TensorFlow and Horowat, for instance, or you can also put it on top of PyTorch, even if you want, or other deep learning frameworks. There's, for instance, Apache MXNet and so on. So also, it's quite nice that it's not so much work, essentially, to do this in Horowat. So it's just a couple of lines of codes, if you will. And we know it's based on MPI, as we were alluding to before. And on top of this, we know that MPI is leveraging the interconnects. Of course, there we know from the previous part of lecture 7, there's this interesting nickel library as well, right? So essentially, implementing this MPI or reduce ring, where we don't have a parameter server anymore, and is a very efficient implementation. Then TensorFlow, of course, as I said earlier, has this kind of parameter server for asynchronous, and then also there's another strategy for synchronous training. So this is something where you can use it, of course, but think about that maybe Horowat is a better way to go, because if you have MPI and then of course also the interconnects. We should also mention PyTorch, which is something I didn't use before here in the lectures very much, because this gets momentum and many people use PyTorch in research and also more and more in training. So this has also a distributed data parallel training part, which you can use, which stands essentially for PyTorch-DDP. Also having, let's say, the general approach like Horowat with the data parallel training and the distributed training, also relatively easy to use. And it's not an additional tool, because basically you use maybe PyTorch already as a deep learning framework builder, building your AI models, your deep learning models, and then with the PyTorch-DDP, you essentially run it then in a distributed fashion. So you stay with the tool if you want. So then let us look a little bit in some aspects on this when you're now thinking about architectures of HPC and communication ideas, single node versus multi-node setups, and so on. Again, I use here this interesting paper that really looked in a lot of papers that published, findings over many years now. And you see here a little bit the time span, from the different years, which gives us a little bit an overview that, first of all, GPUs since 2010, clearly the code you see and the course here it is getting really GPUs oriented, right? So this is distributed learning with GPUs, which is basically the facto standard today. Hence, we also put more and more evidence now here in the HPC course in this, not only for deep learning and machine learning, but also now the distributed deep learning and hyperparameter optimization, which also leverages GPUs, which we will see then in a later lecture 14. So we also can explore that essentially from 2010 to 2017 nicely, that people don't stay with a single node anymore, right? So this was maybe done in the past. You have your own workstation client somewhere under the desk, proudly having, let's say, a GPU or a single node, as you would call it. The people go more and more to multiple nodes in the experiments that you see also here in this, and that doesn't, and I think that that's a very good thing to say, is it doesn't mean that all problems can be always done on multiple nodes, or should be, right? Firstly, we talked about the energy. So is it really necessary? Secondly, you remember the accuracy. So maybe with having just, more and more training on more and more nodes, I don't really leverage the GPU memory anymore. So the efficiency goes down. We talk about this later. And maybe it doesn't make sense. So many problems in machine learning, deep learning, and so on, maybe still fit on a single node. It's just the point that many others, and we see here obviously an increasing number of problems over the last, let's say, 10 years, 15 years, are really going, let's say, to more and more multiple nodes, probably because the models are going bigger, bolder, as we learned, as one of the motivation, or the available data sets get bigger and bolder, and with this require also the use of multiple nodes. So, and with this, we have here another example of the node count, but I think for us important here in the course is really then also the dominance of the communication library MPI, right? So this is in a way very fascinating because MPI has a long track record in physical sciences, numerical methods using known physical laws in computational fluid dynamics, but any other weather, whatever. Examples I have in other courses already, let's say from HPC, and we will explore this not, of course, in our short lecture series coming now from Reza within this course as well. But this is interesting that this MPI then also now, let's say, brings really lots of added value to the AI domain as well. Hence, that more and more people in the AI domain also use high performance computing, right? And we see here different other ways how you can do distributed computing. Some of you know my my cloud computing and big data course that I have at the university. There we go into Spark, Apache Spark. There we talk about MapReduce, which is an interesting paradigm. Let's say Hadoop and so on. And you see the fraction of how this is used over all the years, and you can clearly see that MPI still is a very dominant framework in communication, doing so as we just have learned, for instance, with the MPI all reduce ring, which probably is also here one of the, let's say, added values that you have here, and also has some footprint in the usage of MPI and the dominance. So this is interesting, and of course also good that, let's say, a new domain that is leveraging HPC more and more in these days is actually based on technology that have been created for something different, but is also very much efficient and usable for AI. Hence, an interesting takeaway. And in a way, this lecture is called Distributed Deep Learning, and then can go on and go on. But I guess you get the basics. The whole topic would cover much more time. So hence, I would give you also a link here to one of our trainings we have in the Center of Excellence race, where I teamed up with, I think, a couple of others, like Rocco, for instance, one of my PhD students in the past, now actually graduated. He was also an expert in, or he is an expert in distributed deep learning and has done a seminar with me, which is much older perhaps than this lecture here, but it captures the essence of many other parts I couldn't cover here. And the reason is that I want to give you also some applications, but also some insights in newer learning models, and also, of course, some limits as we discussed as well. Hence, the distributed deep learning in itself needs probably 3-4 lectures these days to really cover it in a more profound way. And I think let's say, proper machine learning course just focusing on this parallel execution might be then in order to look at if you really, want to understand the details. The seminar here is also a good example to start. And you have the paper that I was, let's say, giving you as a reference earlier. And with this, let us look then a little bit also on the limitations that we have, right, by doing this multi-node GPU training. So here we see really the problem that we have with the local batches, right? The more, let's say, we have the data, in these global batch that we would have if we don't do data parallel, for instance, right? So then we all fine per GPU. But if the data is, let's say, and we increase the number of GPUs more and more, then we also see that the local batches would be, let's say, not really filling the GPU, right? So in other words, you would also then consider that the more nodes you have, you basically have to increase the batch size of actually fill the GPUs with data, right? And this is now a key concern. When you now look in the performance of the different, let's say, frameworks which are there. We discussed already PyTorch-DDP. We discussed already Horowat. What we left out a little bit is this interesting DALI that you see here, which is a data loader from NVIDIA, which also brings us quite high performance in terms of data loading. And I would recommend to look at this if you really are an insider. The interesting thing is from the data throughput here, you see they all enable quite a good performance, right? So in a way, if you scale up to more and more GPUs, you see 1024 GPUs, that's beautiful. And the data throughput is, let's say, following suit, if you will. That is quite good. And even if you have here the extended study a little bit with, Deep Speed Native, the other framework that we will also talk about later, Horowat and PyTorch Native, you see that the data loader using that is essentially a key element in it, right? So to keep, let's say, the data loaded, as the name suggests, and then you see also the impact of which tool you use in the end is not so big anymore. Then you see perhaps with PyTorch being the best, but with a data loader from DALI, you can actually have a quite, let's say, good loading of the different GPUs if you, let's say, increase the scaling. However, what you also should now see and get sensitive to is now exactly what you see here, because the more I was explaining this, add the number of GPUs here, there's a key drawback that to give the GPUs that we have more and more also enough to work on, we have to increase the batch size we're going through the data, right? Which you see here, which is still fine for smaller batch sizes. But here is now the key limit I was alluding to, talking about the problem of so-called large batch sizes, that the more you basically then scale up and need this large batch sizes, the lower is actually your accuracy. And with this, the validation accuracy is, of course, a core important part for us. So there's no point of saying, we can have a big batch size and we can scale up to 1,000 of GPUs if, let's say, our validation accuracy is not following suit and falls down so significantly. Hence, you see here sort of a speed spot of saying you can speed up the training, but perhaps only until 8K. Then we have already a problem that the validation accuracy goes down. And what one of the studies from one of my PhD students, now also graduated, Marcel Ach, actually was doing is experimenting a bit with the learning rates. Is an impact, let's say, using the learning rate for this learning in different ways. And can we, let's say, mitigate this problem of the large batch sizes? But this is only possible a little bit, as you see, with the learning rate doing this in an exponential way. Still, we're talking about a validation accuracy, which actually lose quite some performance of the large batch sizes. And there's not a perfect cure for this problem. And you see with this, even if, let's say, Leonardo had, what about maybe 15,000 GPUs available, our problem at hand, while this is, of course, just an example here of an application, our problem at hand will face the problem of the large batch sizes significantly. And with this, we have a problem. You see also another concern in a sense, which not only is a key element in AI with the validation accuracy, is also the efficiency that you see here. Then when you use basically these different frameworks on the one hand, and then also use a number of GPUs. Because then now the efficiency means, do you really use the most amount of memory? Do you use really the computing power of each of the individual GPUs a lot? And depending on the different frameworks, you are a little bit, let's say, better or worse. But here, again, DALI also gives the opportunity to be relatively close to each other that we quite nicely see here, but it's still far from ideal, right? So we're saying we still lose the efficiency the more GPUs we put. So in the end, in this study, that showed also very nicely that you need to have the data to keep, the GPUs also very efficiently running for the training. But at some point in time, when you also increase, let's say, to thousands of GPUs, you will also see the communication overhead, which is another sort of limitation, right? Instead of computing, there's lots of averaging of this ring reduce, there's lots of communication happening. Again, the computing waits, essentially. So the efficiency of the GPU drops because it's not really used. So there are different factors, which in this course we just briefly go through. Again, you have here the reference if you want to learn more. Also, think about the different models have different modus operandi. The residual networks we had already, ResNet 50 as an example, was one where the efficiency is, let's say, quickly dropping. And with other larger networks means more weights, right? More layers. So more to compute. This effect is a little bit slower, but also at some point in time just kicks in as well. Right. So hence, this is another factor. I was always alluding to data or communication. Of course, here we have also the size of the model we were exploring in the beginning, why we do this parallelization. Also here you see sort of the limit of the efficiency breaking down. So this is an interesting study, and in a way, we could also dive into much more in this, but I also promised you some applications here. And some of them that we not really talked about very much is the idea of recurrent structures. And this is a loaded topic because you see it's also alluding to a topic called transformers. I will basically introduce here very roughly because this is a topic I need basically 3 lectures for. But I think it's important to understand the key substance of it because this is fueling the large language models today. However, languages and let's say what we call sequence data has a long history, long before transformers were existing, right? So we basically give you here a little bit of application examples based on different models that have been standing the test of times. And this is a model for sequences called recurrent neural networks. So you see that a little bit here when you want to digest maybe, language. You have a sequence where you have each of the characters part of the sequence. Like also you would have others, right? Medical signals, speech, and so on, or a sentence. These are all sequences of data. And that's where recurrent neural networks are good for, depending on the time, if you have maybe medical signals or on the placement of the words, you have the sequence and you see here this sort of delay that you see here with this recurrent structure that you basically model often here as an unrolling over the time steps. And the same you can do essentially in this illustration where you have then also the activation function showing you a little bit how the time step before influences the time step then according to this kind of loop to itself in a different time step coming in at x1, x1 plus, and so on. And essentially the step before influences then the computing of the next step, which of course makes sense, especially if you now, let's say, have languages, right? So of course, what the character was before has a high impact of what the next character is. So this is a traditional area where, let's say, it's a very specific type of an artificial neural network, not anymore feed forward, right? So this is for sequence modeling with this loop. In other words, you call it a cyclic connection. And there are now new variants on this. One of the ones most known is a long short-term memory. You see having different gates here and different functions that in a way has a certain memory here. You see that through all the different cells, while still the output of one time step is the input of the next, right? So we keep the idea of the, let's say, recurrent neural network for sure. But additionally, we have a sort of memory borrowed from computer science, if you will, that you can manipulate, which is then the idea of this long short-term memory that you can influence. And with this are much better in sequences. And there's even the gated recurrent unit these days that is a little bit, let's say, streamlined in terms of how many gates you really have here. So a bit simpler if you want, but also applies better. And if you now want to think about that these have now different spans of looking at sentences as a whole, right? So these recurrent neural networks do essentially something like a window on it, and LSTMs and GRUs as well. And of course, they have with their memory structure already an idea to be much bigger in terms of what window they can look at the sentence. You see that nicely visualized here. And this will be now also a step where transformers are very different and also good at by looking at the whole space. But we come to this in a moment. I will just leave you on the table one application example again from physics. So you see here an LSTM over time has, interestingly enough, generalized very well to, let's say, unseen structures of water, which is essentially a physical process. But if you learn enough, you could show that the LSTM through its different time steps and sequence data, analyzed again and again, generalized well to unseen elements you throw in the water. And you have the, let's say, example here. Also, if you want to learn more, there are actually quite nice demo videos on the webpage if you want, which is remarkable for machine learning in a way. Because essentially AI, as you know, means learning from data. So we avoid essentially looking at physical formulas that are established already in fluid flow, which you would have, of course, in the idea of computing it purely on the, let's say, equations from physics. And this is, let's say, one interesting example here that I was alluding to, showed that AI can actually generalize well also for physical, let's say, problems where you have, let's say, also the physical formulas to validate and so on. It's not perfect yet, and many people call now new research around, let's say, physics-informed machine learning, physics-constrained machine learning, to even combine the power of both. Coming a little bit to transformers, really very briefly, just to give you an idea that this was, let's say, the key idea of the massive breakthroughs we see now in NLP, in natural language processing. I already, talked with you about the TrustLM large language model, so we don't have to go anymore on this. And the idea how they work is having sort of a transformer encoder and decoder structure, where you have a very specific deep learning model that leverage a so-called attention mechanism, right? So you have a different weights on the significance on each of the parts of the sentence that you have. And GPT and these kind of models that you already know from ChatGPT are based on these models. And the interesting thing is they're basically much better than LSTMs or gated recurrent unit, but they of course also need, let's say, they need very large quantities of data to perform very well. The conceptual idea is really, of course, stays the same, right? We have a sequence of data that you see here on the top, on the right, which is nothing else than our characters, our sentences, and so on that we built according to the language at hand. And the idea how you do this is usually you tokenize the input, right? So you have basically different characters, different sentence, and the transformer models now do this attending or focus on the previous tokens that has been basically generated in a way so that you have, let's say, a better understanding of what happens before. So you see this with the arrows now, right? That come back to your context in a way, they call this, where you can then in the window see a little bit, okay, this aliens, so extraterrestrials like now in the video, is somehow alluding to it. In other words, these transformers have enabled us to look a much bigger, bolder view on sentences, and then give different weights to the previous tokens to attend really to this different problem at hand, and you come through the words. So again, we of course need usually a much more detailed look at this. And there's, for instance, interesting paper here that you can look at again, how that works, how this is essentially then realized. And you see that a little bit here with having the, let's say, encoder and decoder structure again, where the encoder is really this input sentences that you put in that are mentioned, is a sort of representational learner in a way. So it basically gets the input sentences you get in a better representation using this, different multi-head attentions and so on, and you see them stacked up there, coming with the input from the bottom, and then in the decoder structure, you basically use then this representation that you learned in the decoding phase, and then you can basically generate an output step by step based on this representation. Again, think about it like we had in the convolutional network. We said that deep learning is learning also not only, let's say, from the data itself, but also features in the data. Here it's the so-called the representational, the encoding that we basically then have learned, and then we can then leverage to use for building maybe sequences that also is now the point, not only translation tasks, but also as you were, discussing, and as we have, let's say, also discussed a little bit in earlier lectures, generative AI, ChatGPT, and so on, of course, what is then generating new sentences and so on, but actually sound very proper as normal language because we have learned from it. Hence, this is a very important building block, and if you want to understand that really more, you really have to dive more in this paper. Again, transformers might be 3-4 university lectures to really understand them well. So we cannot cover here all the basics, but the attention mechanism, which is then nothing else you learn again right? So you learn this weights again, it's matrices, again, matrix multiplications to learn this and so on. In other words, we can leverage GPUs again very well because we have this, idea of this weight matrices again that we had also before, but here we have it, of course, in a much larger model, which are these transformer models. We use them also for remote sensing, just to say, you see here one paper out of our research. So if you want to know more, you can also go there into a transformer model that is actually used for land cover mapping there and also to, enhancing the training set. And of course, there's a survey here on the right side, which is quite also interesting maybe for you to look at because he's making the large language models much more in detail reviewed and surveyed than I can here actually as part of this lecture today. At the end of the lecture, also just a hint that there's more and more of these deep learning frameworks. So DeepSpeed came from Microsoft in 2020. You have seen we have included this in some of our studies, which sometimes works well and has a, let's say, inherent concept of layer pipelining, being essentially prepared for larger and larger models. So essentially here you see there's a third item, and here essentially the pipeline parallel complementing the model parallelism in a more or less, if you want, 3D structure, because it's also, of course, having parts of the data parallel. So in a way, combining many of the things we've seen here in a smart way, what DeepSpeed is delivering, being itself more or less based on PyTorch, but also being ready then for trillion of parameters and so on. So have something to look at, especially now in the future. Then other frameworks exist like Heat. There's a Ray seminar if you're interested on YouTube, Tarantella, Colossal AI. So many people work basically on this problem of data, having distributed deep learning requirement. And to give you a reference maybe of some elements which happen also at Google AI and so on, I think there's another concept also that you maybe want to look at is local updates here. I leave you this video. It's quite also comes back to the idea of data parallel training, so reviews the concepts. So it's a quite interesting video maybe for you to look at. So in a way, I leave you here. That's all I have to say. And we will now basically return to application spaces with Razor. The postdoc that we have in our research group will now do with you a walkthrough of some short lectures really from 8 till the end in the next couple of weeks to go through the application space again and to explore where deep learning, where physical sciences meet HPC and so on. So have a good journey and see you at the end of the course for the epilogue.